Hello, so we have arrived now at the 25th lecture in our physics of materials lecture series. So in the last class we specifically looked at more and more detail of the way in which electrons are distributed across energy levels, and particularly we try to figure out if there is a way in which we can write an expression for the density of occupied states. Okay, so we found out that there is such a thing as a density of allowed states, and then if you multiply that by the probability of occupancy, we get something called the density of occupied states. Okay, so taken together, that is the picture now which conveys to us what we have in the system as a function of energy. Okay, so we originally had the general idea that as the energy goes up, you fill in electrons, and then you will reach some eventually you will reach an energy level where you have run out of electrons, and that then constitutes the system. And all this of course comes about because we have incorporated Pauli's exclusion principle into the picture, and so we say that first of all at any given energy level there are a finite number of states, and since Pauli's exclusion principle applies, we cannot place all the electrons on just a finite number of states if you have a very large number of electrons, which is typically the case in a solid that we are dealing with. Okay, so 10 power 28 electrons per meter cube is the kind of situation we are dealing with. So we wrote this equation for energy. Okay, so it is simply h bar square k square by 2m. Now today what we will do is we will actually explore a few other ideas associated with what we have done so far, and see what additional understanding we can get of the subject, as well as a better feel for the kinds of quantities that we are currently discussing. Okay, so and this is important because some of the quantities we have discussed, mentioned so far, are quantities that we have not really dealt with perhaps in our high school physics or even early college physics. So therefore these are all new quantities. It is worth our time to actually try and understand maybe how they relate to other aspects of what we know, and also what is the significance of some of these quantities. Is it of any relevance? Is it simply something that is an interesting term that is around, or is it something that is going to be significant for some usage a little later down the road? Okay, so this is something that we want to understand. So we will at least initiate our discussion today on along those lines, and depending on how far we proceed with that, we will elaborate on specific aspects associated with the quantities. Okay, so we write this equation down. E is h bar square k square by 2m. It is simply the square of the momentum by 2m. So that is what we have. K is the wave vector. We call it wave vector. So in principle we can, if it is written in vectorial form, this is the modulus of it. We did most of our work in one dimensional case, so that is why we have we have the results we have discussed so far have tended to have simply the x component of whatever it is that we were discussing, and only where necessary we brought in the other components. We will continue with that in that same spirit in the discussion that we will do today. So wave vector, you will see immediately that first of all it has the units of 1 by length. Okay, so this is wavelength, so this is in meters. I mean meters in meaning it may be 10 power minus 10 meters if it is in angstroms, but still the dimension is in meters. So the dimension of this is length minus 1. Okay, so that is the dimension of it. L minus 1, meter minus 1 is the dimension of it. Okay, so L minus 1 is what we are looking at. And I also mentioned in the last class that when you look at these quantities and they have certain relationships, we can plot information in any one of those variables, based on any one of those variables. Okay, so you have something on the left hand side, something on the right hand side, and so you can plot the expression on, and you have multiple relationships valid for, because you have different variables. So the same information can be presented in terms of the various variables that we have recognized, and based on how they relate to each other. Okay, so depending on which variable you choose, the plot that you make may look different. Okay, so that is a point I made last time, I want to emphasize it again. based on the variable you choose, the plot that you make may look different because it is a different variable, it is simply a plot of different variables, but the information that you can always extract out of it will be the same. Okay, so so that is the thing that we look at. Okay, so in some diagram energy may show up as a flat line. I mean, you may just see if you write energy versus position, it will simply show up as a flat line, for example, at for some a free electron or some such thing. Whereas if you were to plot it in some other variable, you will see a certain different surface where the surface may not be flat, but the surface corresponds to a constant energy. Okay, so that is the point that I wish to make. So based on the variables you choose and the kind of plot you make, the topology of the plot may look different, but the information will be the same, right. So in this case we have energy as a function of the wave vector. Okay, so in fact you can plot it in this is called, so this is simply k. So we say that we can make a plot of we can plot our information in k space. Okay, so we can plot our information in k space, in which case we are actually looking at the components of this information in kx, ky and kz, right, and then we make a plot of this information. So simply again k square will be kx square plus ky square plus kz square. Okay. So if you now see, if you compare this equation here with the fact that you can actually write it down in terms of its components in kx, ky and kz. So we have in fact analogous to that, we had this discussion with respect to quantum number space in our previous class. It is essentially the same comment that we have in with respect to what we are seeing here, and that is simply that you have energy which is a constant, or we can choose a particular value of energy, let me say, put it that way, we will choose a particular value of energy and we can write this relationship saying h bar square by 2m into kx square plus ky square plus kz square. Okay, so you can write it this way. Now in this h bar is a constant, it is simply the Planck's constant by 2 pi, m is a constant because that is the mass of the electron. So these parameters here are all constant, and let us say I would like to do this calculation for a fixed value of energy. I will just say that this calculation I am doing for a fixed value of energy. When I make that statement, what I am essentially saying is that kx square plus ky square plus kz square has to now become a constant, because this is already a constant. I am saying left hand side is a constant, therefore this term has to become a constant. When you do that, what you have is you have a spherical surface, you are defining a sphere in k space. Kx square plus ky square plus kz square equals a constant is the equation of a sphere in k space. K space is simply a plot of all information in kx, ky, kz coordinate system. Okay, so axes are kx, ky and kz. If you make kx, ky, k and z and then you plot whatever you wish to plot in terms of those three variables, then you are plotting the information in k space, and if you plot this information in k space subject to the constraint that you are talking of a fixed value of energy, then you will get a sphere. Okay, so that is basically what we have. So now in other words, if I make this plot here, so we will say this is kx, this is ky and this is kz, right, and then I arbitrarily define some energy value I would define. So what I will see is I will see a sphere corresponding to that. Of course in a 2-dimensional board that I am drawing, it looks like a circle to you, but basically it is a sphere centered around the origin. Okay, it is a sphere centered around the origin, and these are wave vectors. So they can actually be in any direction, it is a wave vector. So it depends on the direction of the movement of the electron, so to speak. So you have a sphere around the origin. Now we also mentioned that in our plot of the n of E or density of occupancy, and also our plot of the Fermi Dirac statistics itself, we said that in the ground state, as it is described in physics, in the ground state, in meaning the lowest energy state of the system, and essentially in this case at 0 Kelvin. So at 0 Kelvin, this is the manner in which the density of occupied states is behaves as a function of energy, okay, and this energy where it drops to 0, the density of occupied states drops to 0, is the Fermi energy EF, okay. EF is one energy where it drops to 0, that is in fact where the Fermi Dirac statistic also drops from its probability of f of E equals 1 to f of E equals 0. So Fermi energy is defined as that energy at which it below which f of E is equal to 1 and above which f of E is equal to 0 at 0 Kelvin, okay. So at 0 Kelvin, at any other Kelvin it would work out to f of E equals 0.5, but below at 0 Kelvin it is it's exactly a step function there, it goes from 1 to 0, okay. So we have E of f, that is the Fermi energy, EF equals Fermi energy. Right. So this is something that we recognize now, that for the system that we have been discussing all along, simply by nature of how electrons distribute themselves across the various energy levels and the constraints we have placed on the system in terms of the number of energy levels, the fact that it has energy levels, that they are quantized, that there is a fixed number of states and so on, based on all those constraints and the fact that we have finite number of electrons and finite number of states, we will always find that there is an energy value above which the occupancy drops to 0, and that energy value we have defined as Fermi energy, okay, and that is the highest energy level occupied by electrons at 0 Kelvin. So okay, so it is the highest energy level occupied by electrons at 0 Kelvin. Now so obviously for our system, the Fermi energy given as a particular system, any system that we take, you take silver as an example, you take copper as an example, that then forms the system, that based on the normal standard way in which copper behaves or silver behaves, we will have a certain number of and based on its density, its actual density and so on, we will have a certain number of free electrons per unit volume. So that is very specific to that system, okay. So that is very specific to a given system, so we can define that for the system that we are interested in, and on the basis of that definition we can write figure out what will happen as you fill electrons at various energy levels. So for every specific system that we discuss, at a particular value corresponding to that system, which will be unique to that system, at that particular energy value you will run out of electrons, okay. So in other words, based on the system that we choose, we will have a specific value of Fermi energy, okay. So it is not that the Fermi energy is the same regardless of which metal you choose or regardless of which crystal structure you choose and so on. When you change the crystal structure, when you do something else, you are changing, perhaps you are changing the number of free electrons per unit volume, perhaps you are changing the density of the material and so on. So in all these things there are a lot of changes that are likely to occur, therefore from material to material the value of Fermi energy need not be the same, if at all it is going to be quite an accidental match, okay. So it is in principle it need not be the same, and even for the same material, as you change if you put it under different circumstances, maybe the phase changes and so on, if the density changes, if there are additional changes that are occurring in the material that affect the number of free electrons per unit volume, then you may have a change in, if it also affects the way in which the energy levels are in the system, it can affect the Fermi energy, okay. So the bottom line is it is a fixed value for a given system under some circumstances, okay. So therefore a Fermi energy is a constant in some ways for that particular system under those circumstances. So for a particular system you can uniquely identify a particular value of Fermi energy. So for that system, when you make this plot kx, ky, kz, if you plot energy of the various electrons that are present within the system in this k space, then you can make several spheres, each sphere will consist of all the electrons that possess the same amount of energy, okay, and finally you will reach a sphere which is at some size, you will reach a sphere here where kx square plus ky square plus kz square times your value here h bar square by 2m, h bar square by 2m times kx square plus ky square plus kz square for this particular sphere, this larger sphere that I have drawn here, for this sphere h bar square by 2 m into kx square for this particular sphere will be equal to this value of EF. Okay. So, for this particular sphere, not for the spheres that are below it, for the spheres that are below it they are all also constant energy spheres, but they are for energy values less than EF, less than the Fermi energy. For this particular sphere the value of kx square plus ky square plus kz square times h bar square by 2 m will work out to EF. Okay. This sphere in K space, okay, this sphere in K space is called the Fermi surface. Okay. So, now we have two concepts that I have just we have discussed so far. One is the existence of this energy called the Fermi energy and its significance, the fact that you, when you run out of electrons you reach this that energy value where you are running out of electrons becomes the Fermi energy, and therefore it corresponds to the electrons, it corresponds to the energy of the highest energy electrons in the system. Okay. So, because you are putting them from the lowest energy upwards, highest energy that that you run out of electrons is the Fermi energy. That same energy you can plot because of its relationship to the wave vector that is there in the system, based on its relationship to the wave vector, based on its relationship to the wave vectors of the electrons, right. These are not some arbitrary wave vectors, these are the wave vectors of those electrons which have this energy. Okay. So, based on this relationship you can identify a certain surface in K space which consists of kx, ky and kz axes, right. That surface will turn out to be a sphere simply because of the nature of this equation, and that sphere is referred to as the Fermi surface. Okay. So, a sort of a plot we can now see and it has a certain shape and everything, and that is the surface which is the Fermi surface, and there is an energy corresponding to it called the Fermi energy. So, these are two concepts. There is one other concept that we can look at. We will now see the significance of these. In just a moment we are going to discuss the significance of all of these. So, we right now I am only defining those quantities, I am defining them and trying to explain what it is and where they have come from. What is the use of this surface, what is the use of this energy, what is it that we can say about the system based on these energies, that is another piece of information which we will talk of in just a moment. There is one other quantity which we will define in relationship to this information that we have put down here. Okay. In general, in systems where you have, you know, when you are discussing thermal energy of the system and so on, we essentially associate energy, we will put it down here. Okay, we will keep it here so that we can follow it. Energy on a per particle basis is given by Kb times T. Okay. So, in fact when we did our we would have come up with something similar, the translational kinetic energy when we did Maxwell-Boltzmann statistics and when we did the ideal gas behavior came out to 3 by 2 kBt, half mv square is 3 by 2 kBt is what we came up with. So, it essentially relates to kBt, that is the basic idea, the energy relates to kBt, okay, some constant is there, it relates to kBt. So, now similarly we can write EF. So, this is all on a per particle basis. So, in our case the particles are electrons. So, we can write EF equals Kb times T some T, which in this case we will put subscript F Tf to associate it with the fact that it is EF that we are equating it with. Okay. So, EF is Kb times Tf. Okay. So, that is just based on the general relationship between temperature and energy on a per particle basis for the kinds of system that we are looking at. This Tf is referred to as the Fermi temperature. Okay. So, Tf is the Fermi temperature. Okay. So, what we see are, we have three quantities or quantities and say surfaces that we have. The first is Fermi energy, which is E subscript f, the second is Fermi surface, which is a sphere in K space, the third is Fermi temperature, which is T subscript f, right. So, we have these three things, Fermi energy, Fermi surface, Fermi temperature. So, these are all definitions that have come about as a result of the kind of system that we have discussed, the phenomena in the system, how they relate to each other and so on, and with respect to some other definitions that we have. So, on that basis we have come up with these three definitions. Okay. So, now we will look at each of them one by one and try to understand what is the significance of these three definitions, these three terms, and what can we say based on these three terms. I mean, what if in a system you get this information about the system, what is it that you can sort of relate it to. So, and what is the kind of issue that we have with it, what is the utility of it. Okay. So, where can we use this information, how does it help us understand something about the material property, how does it help us make some predictions, where in the process of making the predictions where is this information going to appear. So, this is a sort of, this will sort of lay out for us, this discussion will sort of lay out for us where we can expect these quantities to show up in some of our later classes, and perhaps to understand what is the manner in which it will show up, and what is the level of significance of this quantity. Okay. So, that is what we are going to look at. So, we will start with Fermi energy. Okay. To discuss Fermi energy, to tell you something more about the Fermi, we already know that when you place electrons from the lowest energy level upwards, the highest energy level that is occupied is the Fermi energy. That is the definition of Fermi energy at 0 Kelvin, right. So, we will keep that definition in mind. We will look at a few other quantities that we are more familiar with, and then we will come back to Fermi energy, right. So, let us look at, say, temperature, just temperature in general. Okay. Now, temperature, if you look at the thermodynamics associated with temperature, when we say temperature, what we are saying is it is the potential, it represents the potential for heat to leave a system. Okay, represents so you can think of temperature as being the potential of heat. It is a measure of the heat in the system, but more importantly it is a measure of the potential for heat to leave the system. In other words, if you bring two objects of different temperatures next to each other and bring them in contact with each other, whichever has a higher temperature has a greater tendency to get the heat out of the system. Both of them have a tendency to both of them have a certain potential to get the heat out of the system. The temperature is a measure of that potential. The higher the temperature, greater is the potential for heat to leave that particular object. So, you bring two objects together, whichever has a higher temperature, it will push heat into the whichever object has the lower temperature. Okay, and therefore potential can be described as the temperature can be described as the potential for heat to leave the system, and higher the temperature, higher is the potential for heat to leave the system. Okay, so this is something we talk of in thermodynamics, and and therefore we may or may not have thought of it in specifically these lines, but that is the way, that is a reasonably good way of saying it. Similarly, if you look at pressure, it represents potential for material to leave the system. And usually you are talking of a liquid or a gas or some such thing, and so basically when you have two objects with differing pressures, or you have two containers where the species are at two different pressures, so you put a pressure gauge on one, pressure gauge on the other, you see that they are two distinctly different pressures. So whichever container has the higher pressure, there is a greater potential for the material within that container to leave that container. Okay, so as long as there is pressure, both of the containers have a material which can leave the container, but when you connect the two containers, whichever has higher pressure has higher potential to for the material inside that container to leave it, right. So therefore that is how that is how pressure equilibrium arises. So when you connect those two containers, more material will leave one container, the container which has higher pressure, and move to the container which has lower pressure, thereby reducing the pressure of the container which was high, increasing the pressure of the container which was low in pressure, till the pressure in both the containers equalizes. When pressure in both the containers equalizes, the tendency for material to leave the first container is the same as the tendency for the material to leave the second container. At that point you reach equilibrium, right. So that is how it happens. Same thing is true for temperature. When the heat moves from one body to the other body, the hotter body to the colder body, when it does so, the temperature of the hotter body will come down, temperature of the colder body will go up, till such time that the two temperatures are yet to equilibrate. When the temperatures equilibrate, when you have the same temperature in both the objects, then the potential for heat to leave the first object is the same as the potential for the heat to leave the second object. Then heat transfer becomes equilibrated. Any heat going from one side to the other is equated by the heat going from the other side to the first. Then you reach an equilibrium. So that this is what it is. The third quantity, so we write this as T, we write this as P. There is another quantity called chemical potential. Okay. Chemical potential is typically designated by mu. Now chemical potential of it is usually associated with a particular species. Okay, so in a more metallurgical material sense, you may have you know, let us say you have whatever, you have iron which contains say carbon in it. Okay, so you have iron containing carbon in it. So we will associate chemical, we can designate a certain chemical potential to the carbon present in the iron. We can also designate it to the iron itself which is present there, the iron atoms that are present there, and so on. So it is assigned to a very specific species. So in your system you may contain lot of different species, you may have a solution where you have several different solutes present. For each solute you can which you are identifying as a species, you can designate a chemical potential. Chemical potential is a measure of okay, it is a measure of the potential of a specific species to leave that phase for which you have in which you have found out its chemical potential. In other words, I can have let us say two different samples. Okay, so two different samples, one contains carbon of a certain percentage, another contains carbon of another percentage. When you typically bring these samples together, our conventional engineering experience is that carbon will diffuse from one sample to the other, right. So it's as long as the percentages are not the same, it will diffuse. We normally simply talk in terms of percentages, but the more appropriate term there is in fact chemical potential. Okay, so and they need not necessarily be the same, that is the important thing you have to remember. Based on the kind of solutions that are formed, those two need not necessarily be the same. In many cases in an engineering sense it works out to be roughly the same, so we can use it that way, that is why we have used percentages in general, but they do not have to be the same. So percentage of a species does not directly equate to the chemical potential of the species, but it is a reasonable measure. So anyway, our macroscopic understanding of this phenomena of diffusion is that diffusion occurs when the concentration of the species in two different locations is not the same. Okay, and as I said, the more appropriate term is the chemical potential of the same species in two different locations is not the same. So chemical potential therefore is a measure of the potential of a species to leave that particular phase. Okay, so whichever that phase is, and go to another phase where the chemical potential is lower. Equilibrium in the thermodynamic sense occurs when the chemical potential of the species is exactly the same in all the phases that are in contact with each other, that are in a position to interact with each other. That is when thermodynamic equilibrium occurs with respect to that system. Now with respect to what we have just discussed, okay, so I have said that we will relate Fermi energy to this, okay. So Fermi energy EF represents the highest energy electrons present within the system, right. So it represents at least at 0 Kelvin represents the highest energy electrons in the system. So what happens is, as you are aware, in general when you bring systems together where the energy levels of some component of the system is not the same, the systems try to rearrange themselves or the component tries to rearrange itself in such a way that energy is minimized. Therefore what normally happens is that when you bring together materials where the Fermi energies of the two samples is not the same, okay, or the two materials is not the same, the electrons will tend to move from the material that has a higher Fermi energy to a material that has a lower Fermi energy, such that the energy of the system decreases, okay. So the Fermi energy of an electron is equal to the chemical potential of the electron. Fermi energy is the chemical potential of electrons at certainly at this is okay, this is in a sense this is an approximation, this is not exactly correct, there is some corrective factors to be thrown in, but for all lower temperature applications, typically the kind of application we are going to be we typically do, this is an acceptable statement to make, okay. So Fermi energy is the same as the chemical potential of the electrons. So higher the Fermi energy of a particular material, it is the same as saying that the chemical potential of electrons in that material is high. Therefore when you put two materials together, the chemical potential, the material with having higher Fermi energy and therefore where the electrons have higher chemical potential will tend to get the electrons to leave the system, and they will go to the material where the Fermi energy is lower, and therefore the chemical potential of electrons in that material is lower till the chemical potentials equate or some other phenomena occurs. So it is a measure of the chemical potential of electrons, and therefore in that context it is a very useful piece of information. It is not simply a definition of just arcane interest, it is a very or of academic interest, it is a very useful measure because it tells us directly about something about what will happen when you bring materials together. So even when when you bring semiconducting materials together, when you try to you make junctions of different materials, this is a very important phenomenon. The chemical potential of the electrons across those various junctions is a very important phenomenon in the sense that there will be an attempt to equate those chemical potentials. So what will happen as soon as you bring two materials together is largely determined by this value of Fermi energy, okay. So therefore it is a very important piece of information. We understand also physically it's an information that is something fundamental about the material because it tells us something about the highest level of highest energy level of occupied by electrons, but it has a very practical application is what I am trying to bring out. So the fact that in a lot of electronics that you will read, what is happening to the Fermi energy, where is the Fermi energy, what is happening to the Fermi energy of the system as you do various things to it is something that is of relevance, okay, is an important part of the discussion that that will exist in most parts of electronics, okay. So therefore this is a very important concept, and this is the way it relates to some other things that you have perhaps been aware of. So that is our first quantity, Fermi energy, and we now understand its significance, that it is quite a valuable piece of information to have about the system, okay. The next thing we will look at is the Fermi surface. Okay. Now the Fermi surface as we saw is a sphere, so we will as we discussed here is a sphere in k space where you have plotted kx, ky and kz, and so we have a sphere in Fermi surface, okay. Now it is, as I mentioned, it basically says that that is the surface in k space that corresponds to the Fermi energy, okay. So it is the surface in k space that corresponds to the Fermi energy. We already just discussed that the Fermi energy itself is a very significant quantity because it represents the boundary, so to speak, of the energy values that are occupied by the electrons, and past which it is a set of empty states at least at 0 Kelvin. So so that is number one. So therefore on that basis itself you can anticipate that this surface may represent something important because it is representing that energy value, right. So therefore you can expect that this can represent something important. Also in K space, what have you plotted? You have plotted Kx, Ky and Kz. These are wave vectors, okay. So and they therefore are of this so K is simply 2 pi by lambda, right. What is this lambda? This lambda is a wavelength, okay. So it is the wavelength that we are associating with an electron, right. We have said that in the quantum mechanical view of the world, view of the universe, we can think of we can look at matter either as consisting of particles or consisting of waves, and so this wave particle duality is an aspect that we have to accept, and based on what experiment we are doing, what phenomena we are observing, one or the other of these behaviors will tend to dominate, or at least we will be able to better interpret something based on one of these phenomena, or more easily interpret something based on one of these phenomena. So we understand that if you have electrons moving within a solid, they have a linear momentum associated with them. Associated with that linear momentum is a based on the de Broglie relationship, we have a wavelength associated with it. So this wavelength corresponds to electrons, the wavelength corresponding to the electrons moving within the material, right. So it is something that is very specific to the electrons. Now and in this particular case it is wavelength corresponding to this Fermi energy, Fermi surface, okay. So the Fermi surface therefore represents all the wave vectors corresponding to that the largest energy electrons that are present within the surface. Now we will see later in one of our other classes, and you are also anyway familiar with this basic idea that when you send in electromagnetic radiation, okay, electromagnetic radiation, when it is sent into a sample, it interacts with a sample, right. So it is on that basis that we have X-rays interacting with matter, we have waves of electrons, electron beams, so to speak, interacting with matter. What is this interaction that we talk of in physics and in material science and engineering? The interaction that is of significant interest to us is the diffraction process, right. So you send X-rays, of course one of the requirements then therefore is that the wavelength of the beam is of the order of the kinds of spacings that exist within the system, only then you tend to see much more of the interaction, but still you will see the at least it should be of that order, it can be less, okay. So you can have wavelengths much smaller for you to see interaction, but at least it should be of that order. So so we see that we are aware that that there is diffraction processes that occur, right. So when a diffraction process in a conventional sense, when you are used to diffraction, what we have is a sample that is separate, okay. So you have a sample that is existing separately, so some sample some source of radiation, so some radiation from a source is impinged on a sample, and then we have some detector, okay. So based on the experiment you are doing, the exact position of the source, the position of the sample, the position of the detector will change. They do not have to be in the configuration that I have just shown you. You can have a source on top, you can have a sample in the middle, and you can have a detector at the bottom. So you can have all these possibilities, okay. So there are several possibilities in how this can be arranged, but the basic idea is that you have a source of radiation, it sends in electromagnetic radiation, which is then which then impinges on the sample, and then what comes off of the sample is captured in a detector, right. And then based on what we typically find is when diffraction occurs, you will find that as the detector is moved or as a function of position, you will find maxima or minima. You will find that there is constructive interference in some directions, there is destructive interference in a lot of the other directions, and based on the periodicity of the sample, some places you have constructive interference, some places you have destructive interference. So very strong signals in some particular locations of the detector, and very and essentially zero signal at other locations of the detector, right. So this is the diffraction process. So the diffraction process essentially requires a few requirements, I mean few points that have to be satisfied for diffraction to occur. First of all, you have to have electromagnetic radiation for in the sense that we are discussing it at least. In a general sense, these are the ones we are looking at. 2, you need to have a sample that has a periodic structure. Okay, a sample that has a periodic structure, and therefore we are basically talking of some crystalline sample. Okay, so we want a crystalline sample, right. So some kind of a periodic structure has to be there, some crystalline sample has to be there, and the wavelength should be wavelength should be of in a range that enables be identified, to be recorded. Okay, so it simply has to be in a range that permits us to record the diffraction effects, and at least which typically means it has to be at least in the wavelength should be at least in the order of magnitude of this of the spacing in the crystalline sample, if not less. Okay, so that is what we are looking at. So these are the general requirements, and the typical way in which we are used to seeing diffraction in labs is that you have a separate sample, a separate source, a separate detector, and that is how you see diffraction, right. But nowhere in this set of requirements have we stated that. We have never really stated that the source should be somewhere else, the sample should be somewhere else, the detector should be somewhere else. That is just an experimental convenience that we have ended up doing it that way, but we have not there is no real fundamental requirement that the source has to be somewhere else, the sample has to be somewhere else, and the detector has to be somewhere else, right. It is only an experimental convenience. So therefore if you already have waves within the sample, if you already have some kind of behavior of particles within the sample which is equivalent or if not exactly equal to an electromagnetic wave radiation passing through the sample, then the basic idea that diffraction can occur will still happen, alright. So to restate it, if you have particles within the sample which are showing you all the characteristics of electromagnetic radiation based on their behavior, right, then those particles and the electromagnetic radiation behavior kind of thing that they are demonstrating can also interact with the periodic structure of the sample within the sample to show you diffraction effects. Okay, so this is something that can be expected, there is nothing here that says that cannot hold true. So what in our particular discussion, what do we have? We have a sample that has electrons inside it, those electrons have energy, and based on the energy and momentum that they have a wave vector associated with them, alright. So that is the wave vector that we have designated as this 2 pi by lambda or k. So therefore we find that within the sample you have electrons that are moving, there is a wavelength associated with them, and so we now have the equivalent of electromagnetic radiation within the sample, if you want to call it that. Okay, you have an equivalent of an electron beam within the sample. So you need not specifically have an electron beam from outside. When we do electron diffraction in an electron microscope, you have a source of electrons from outside, it sends an electron beam, it goes through the sample and it shows you diffraction, right. Whereas here the source of electrons is with the sample itself, the electrons are within the sample, they are moving around, but they have all the other characteristics, they do have a wavelength associated with them, and based on the wavelength you may or may not have diffraction based on the spacing of the planes here. Therefore when you look at the Fermi surface information that we have discussed, The Fermi surface is of use to us because it represents the wave vectors of the electrons, it represents all the possible wave vectors of the electrons from the lowest energy electron to the highest energy electron, right. So and this is reciprocal length space. In this same space we can also plot the periodicity of that crystal structure that we are talking of. So when I take a particular sample, there are two pieces of information that are unique to that sample or specific to that sample. One is its crystal structure, which means what are the axes, what are the dimensions and so on of those axes, unit vectors and everything. So that is an information that is length scale information, and we can plot it in a manner that it will fit into this K space. We will discuss that plotting little later, but that information, so the periodicity of the lattice can be plotted on this picture and it will represent the periodicity of the lattice. The wave vectors permitted by the system based on the number of free electrons available in the system can also be plotted in the same plot, and when you plot the two of them together, in other words when you plot the Fermi surface as well as the periodicity of the lattice together on the same picture, what we will see is we will be able to identify conditions under which the electrons which are present within the material will undergo diffraction because of the crystalline structure of the same material, okay. So this is a very important phenomenon, okay. We will explore this in one of our upcoming classes by putting numerical values against it, but and making diagrams, these same diagrams that I have just described will be made in those classes, and we will look at the numerical values associated with it. But as a concept, what this represents is that there are certain energy values that the electrons can have corresponding to specific K values that they can have, at which point their interaction with the crystal within which they are, crystal structure within which they are, results in diffraction, okay. It is this diffraction process that now results in energy values that are permitted or forbidden for those electrons, okay. That aspect we will elaborate on in one of our later classes, but as a concept I wanted you to at least be aware of it at this stage, and therefore the Fermi surface which now represents the highest energy electrons becomes a very important parameter, okay. So we now have an understanding that Fermi energy is an important parameter. We also have an understanding of what the Fermi surface is, and the fact that Fermi surface is also a very important parameter in our ability to understand material properties. The last thing I will talk about is the Fermi temperature, which I just very briefly touch upon today, because at least we only we will just say what it is, and when it becomes when we use it in our next class, we will actually use it. At that point you will get a better sense of what it is. As I said, it is simply, if you write Kb Tf equals Ef, you will get a value of temperature, okay. So it is a temperature corresponding to okay, it is a temperature corresponding to the Fermi energy. The point I want to highlight here is that if you actually did this calculation at 0 Kelvin, let us say the material is sitting at 0 Kelvin, the Fermi energy will be of the order of few electron volts, okay, several electron volts it will be. So if you take that and you just put in the value of Kb and you do this calculation, you will find that the temperature, what is being designated as the Fermi temperature, will work out to be a very large temperature actually. It will be several thousands of Kelvin, okay. So 5000 Kelvin, 10,000 Kelvin, something like that. It is a very large temperature, but we are doing this so in a way it is initially very confusing to look at, because we are saying that the material is at 0 Kelvin, okay. So or it is at its ground state, it is the lowest energy state. You will find that the Fermi temperature will work out to be a very large number, very large number. The significance of the Fermi temperature we will see in our next class, but the basic point here is that what we are essentially saying is that when you arrange the electrons in various energy levels, if we assume that a given energy can only be present in the form of thermal energy, then we can sort of equate it to a temperature, and that is what this temperature works out to for the highest energy electrons in the system, okay. So that is what this temperature works out to. And how do we rationalize it? How do I say that something is sitting at either 0 Kelvin or very near 0 Kelvin, but the temperature of electrons there is several thousand Kelvin? How do we rationalize this? Well, basically the idea is that when you talk of temperature, we typically don't talk of temperature of a single particle. In this case we don't talk of a single electron, we are looking at the average temperature of the entire system. whenever you do that there is a distribution of energies and therefore a distribution of temperatures, okay. So it is always like that and you end up taking the average. So the average is sitting at 0 Kelvin, a very tiny quantity of electrons which constitutes a very tiny quantity of the material present in the system is sitting at a very high temperature, or it can be thought of at least in that context. And so that is how you can rationalize this idea that you have something sitting at very low temperature, but it has a Fermi energy which has a temperature corresponding to that Fermi energy which is a very high temperature, okay. So we have, in this class we have looked at these three important quantities, what they are, how they have come about in relation to everything that we have discussed so far, okay, and what they represent, what is the importance of them, what is the physical significance of them, and we find that they are all very relevant quantities. So we will halt here in this class. In the next class we will look at a calculation that as I mentioned we need to look at specific heat some more. So we will start our discussion in the next class using specific heat, where we will suddenly see that this Fermi temperature becomes of relevance, and then in subsequent classes as we develop better, even better models for our materials, we will actually use these Fermi energy and Fermi surface and the interaction of the Fermi the electrons in K space in the plot that I was discussing with the periodic nature of that material, and on the basis of that interaction we will draw much better conclusions, much more what shall I say, informative conclusions of how the material behaves and why it behaves in that manner, okay. So with that we will halt for today. Thank you.